Hi, this is Wagner Kamakura. In this tutorial, I'm going to show you how latent class analysis can be done using my analytic tools for Excel. But before doing that, I'm going to give you a sense of how latent class analysis works. At this point, I hope that you have already gone through my tutorial on k-means clustering, because the k-means clustering algorithm is very similar to how latent class analysis is estimated. If you recall, in the k-means clustering algorithm, the first step is to generate k-random means for all the variables for each one of the k clusters you want to create. Then you assign each case to the nearest mean based on Euclidean distances. Recalculate the means, reassign each case to the nearest mean again, recalculate the means, and repeat this process until from one iteration to the next, the means don't change that much. And we're going to see that this iterative process is not that different from what we're going to do in latent class analysis. K-means is definitely the most popular tool for classification because it's computationally efficient, handles a very large number of cases, and a very large number of variables. But the k-means clustering has its limitations. The major limitation is that it requires a metric, Euclidean distance, to measure similarity between cases and to assign cases to clusters. That kind of metric works well for continuous variables such as age and income, but it doesn't work very well for discrete categorical variables such as gender and marital status. How would you calculate the distance between a single male and a divorced female? That Euclidean distance is not meaningful. And that creates a problem for the classification of cases to the nearest mean. Another limitation of k-means clustering is that it's not very robust for missing data. If one case has some missing observation, it's not that clear how you would classify the case to each one of the clusters. And aside from that, there's no clear statistical criterion to choose between cluster solutions. Latent class analysis operates in a similar fashion, but the cases are classified into groups based on similarity in data patterns rather than based on Euclidean distances. And this is done through the use of probabilities. And because the classification is done in probability, latent class analysis applies to virtually any type of variable, discrete or continuous, or even censored, as long as you have some univariate probability distribution for each variable. And because the model is based on probabilistic assignment, missing data is not a major problem as long as the data is missing at random, something that we are going to see in a few minutes. Latent class, as I mentioned, is a probabilistic classification algorithm, so that each case is classified to the classes or clusters in probability. So in this example, John is most likely a member of class 3, Mary is most likely a member of class 1, but has some probability of belonging to class 2 instead of 1. The probabilities here reflect our uncertainty about where each one of the cases really belong to. To understand how latent class works, let's consider this simple example. We have a large sample of voters, Joe, Mary, Jane, etc. And for each voter, we know 3 characteristics: whether the voter is married or single, male or female, Republican or Democrat. We want to classify a sample of voters into latent classes. In our simple example, there are at most 8 groups of voters: 2 marital status times 2 genders times 2 parties. However, because these 3 binary variables tend to be associated across voters, observed data might be reasonably well explained by less than 8 types of voters. Those groups are what we call latent classes. For example, it might be possible that women are more likely to be Democrat than men, and married people more likely to be Republican than Democrat. If that kind of association happens, even though there are at most 8 groups of voters, with 2-3 groups, we might be able to explain most of the associations observed in the data. And those groups are what we call latent classes. So because there is association among the observed categorical variables, it is possible to classify all cases into a relatively small number of latent classes. So that within each latent class, the observed categorical variables are independent, and the association among these variables over the entire sample is captured by the differences across latent classes. The whole idea here is to capture the association among the observed variables in the population through these latent classes within which the variables are independent. To continue our simple example, we have three indicators here: marital status, gender, and political party. And they're binary, so that if the probability of being single is S, the probability of being married is 1 minus S. If the probability of being female is measured by F, the probability of being male is 1 minus F. And let's assume that we are interested in identifying two latent classes, class 1 and class 2. Since there are only two latent classes, the size of class 1 is represented by pi. Since we only have two classes, the proportion of people in class 2 would be 1 minus pi. These latent classes are going to be described by three probabilities. We are going to describe class 1 in terms of the percentage of singles in class 1, percentage of females, and percentage of Democrats in class 1. So S1 is the percentage of members of class 1 who are single. P1 is the percentage of members of class 1 that are Democrat. Same thing for class 2. And they also can be interpreted as probability. Given that somebody belongs to class 1, the probability that that person is a single is S1. The probability that that person who belongs to class 1 is female is F1. And as I mentioned before, pi is the relative size of class 1, proportion of all voters in the population who belong to class 1. To build our latent class estimator, which I said is somewhat similar to the k-means algorithm, we need to define this concept of conditional likelihood. Assuming that within each latent class, the variables are independent, we want the variables to be independent within each class because we want the classes to capture the relationship among the variables over the population. Given that the variables are independent within each class, the likelihood of finding a single male Republican who is a member of class 1 is the probability of being single in class 1, which is S1, probability of being male, 1 minus F1, times probability of being Republican, 1 minus D1. The likelihood of being single male Republican, given that you belong to class 1, is S1 times 1 minus F1 times 1 minus D1. The likelihood of being a married female Republican, given that you belong to class 2, is equal to the probability of being married, 1 minus S2, times the probability of being female, F2, times probability of being Republican, 1 minus D2. Now that we know how to calculate the conditional likelihood, we can do the flip side of it. Calculate the posterior probability that somebody, a voter, belongs to class 1, given what we know about that person. So now we're flipping the problem. How can we classify a person to class 1? If we did not have any information about that voter, we could say, without any information, the prior probability that that voter belongs to class 1 is the size of class 1, pi. Given additional information, we know that that person is a single male Republican. Now we can use that information to update our prior to calculate the posterior probability. So the posterior probability that the voter belongs to class 1, given that that voter is a single male Republican, will be equal to the prior, which is pi, times the conditional likelihood of finding a single male Republican in class 1 over same thing as the numerator plus the prior probability of finding a person in class 2 times the conditional likelihood of finding a single male Republican in class 2. That's the base rule. So now we know how to classify a voter into latent class 1 or 2, given the observed data. So in this particular example, the observed data is that the voter is a single male Republican. Given the current parameters, pi, S1, F1, D1, S2, F2, G2, the posterior probability that this single male Republican belongs to class 1 is equal to pi times S1, 1 minus F1, 1 minus D1. Prior times conditional likelihood. Same thing here on the denominator, plus the prior probability of belonging to class 2 times Probability of finding a single in class 2, probability of finding a male in class 2 times probability of finding a Republican in class 2. Now we know how to classify a voter into the latent class given the observed data. Now we have all the requirements to estimate the latent class model. We have the data, the marriage status, gender, and political affiliation from a sample of voters. And we have the Bayesian rule to classify voters into the latent classes. And we do this using something that, as I said, looks a lot like the k-means algorithm. First step, randomly assign cases to classes. So we randomly generate probabilities. Pn1 is the probability that voter n belongs to class 1, a random number between 0 and 1. P2n is the probability that that same voter belongs to class 2, which is just 1 minus P21. And that's the probability of belonging to class 1. The complement is the probability of belonging to class 2. That's first step. Now that we have some information about who belongs to what class, we can calculate the percentage of single female Democrats in group 1, the percentage of single female Democrats in group 2. Those are our conditional probabilities. What is the conditional probability of finding a single, a female, and a Democrat given that we are in group 1? What is the conditional probability of finding a single female Democrat in group 2? We do this by weighting the actual data by the membership probabilities. And we also compute the size of group 1, pi. So that's equivalent of calculating average in the k-means algorithm. Once we have probabilities within class 1, probabilities within class 2, and the size of the classes, the next step is to compute new class membership probability. In other words, classify each case to class 1 and class 2 based on the data and based on our current estimate of S1, F1, D1, and pi, S2, F2, D2. We do that classification, repeat steps 2, 3, 4 until it converges. The end step is equivalent of calculating averages. The E step is the classification. The difference is that instead of averages, on the end step we have probabilities, and instead of distances for classification, we use conditional likelihoods and the Bayes theorem on the E step. What is the advantage of using probabilities instead of distances and means? First of all, the cases can be classified into the latent classes even when some of the data are missing. Suppose that this particular voter did not disclose marital status. Voter said, my marital status is none of your business. We can still classify that voter into group 1 or group 2 based on all the other available data. We have the posterior probability times the probability of being male times the probability of being Republican, given that you belong to class 1. And from that, you can get the posterior probability that the voter belongs to class 1. That way, the parameters can be estimated even when there are missing data. Typical k-means clustering, you have to eliminate cases when there is one missing variable for that case. In latent class analysis, we are going to make use of all the available data. No need to eliminate cases or variables. On top of that, the probabilistic assignment case into classes will be based on all the information. If you don't know marital status, you just skip marital status. You're still going to be able to classify. Of course, there's going to be more uncertainty, but you can measure that uncertainty, which is the last advantage of latent class analysis. Because it's a probabilistic model, we have statistical criteria to evaluate the quality of the solution. You can measure how uncertain was the classification to each case to the classes by measuring the overlap. It's a measure of entropy. And a value of 0 means that the classes are perfectly separated. Each case was classified with probability 1 to one class and 0 to all the other classes. A measure of overlap equal to 1 means that there is total uncertainty in the classification. Every case was classified to each one of the classes with equal probability. So you have a measure of how fuzzy, how uncertain was the classification of each case to the classes. And you have a criterion called the consistent archaic information criterion that measures the quality of the solution. To what extent the parameters you estimated, this model has predictive validity. So it's a criterion that tends to penalize models with too many parameters, leading to simpler models. For the consistent archaic information criterion, the smallest value points to the better solution. Let's open my analytic examples and look for the tab Latent Class Analysis containing the example. In this example, we have about 400 consumers who indicated how often they are engaged in different activities in their leisure time. For each one of the activities, their engagement was coded into an ordinal variable of 4 levels, where 1 means the bottom 25% least frequent, and 4 means the top 25% most frequent. And they indicated their engagement in multiple activities, going from attending the theater, going to parties and social functions, reading magazines, reading books, going out with friends, and so on and so forth. And to run latent class analysis, go to add-ins, Kamakura Analytic Tools, latent class analysis, and highlight the data. There we have, it's already automatically highlighted. The thing you need to specify is how many classes do you want. We're going to ask for 3. And here we have a list of all the activities, a list of indicators that we're going to use to identify latent classes. This particular implementation of latent class analysis can handle 2 types of variables, either categorical or ordinal. So if you don't do anything, it will assume that the variable is categorical. Just as an example, I'm going to allow theater to be categorical, but I'm going to assume all the other ones to be ordinal. Click OK, and that's all you need. And here we have the latent class output. First of all, the level overlap among the latent classes is not that high, 29%. It means that some of the cases, like Abelard, are not clearly classified into one class. Some are even worse. For example, Candide. It's not very clear which class it belongs to, while some cases, like Ichabod, are clearly assigned to one class. And this overlap gives an overall assessment of the overlap in the classification of cases into classes. And as I explained before, the consistent Akaike criterion is a measure of predictive fit. And the smallest, the better. And how do we use this? You run the latent class analysis with 1, 2, 3, 4, 5 classes and pick the one that is meaningful to you and also has one of the lowest consistent archaic information criteria. In this example, we identify 3 latent classes. The largest is the second one with 41% of the sample, followed by the third class. And if you recall, I assumed that attend theater was categorical. So we have probabilities associated with each one of the response categories. While all the other items I assume to be ordinal. So what we have here is the propensity to be on the high quartile for each one of the activities. And you can see a clear difference in the lifestyle of these 3 clusters. The 2 automatically highlights in blue the probabilities that are higher than average, and in red, the ones that are lower than average, just to give you some sense of the patterns. And you can see here that class 3, 34% of the sample, tend to be engaged into party social functions, going out with friends, reading newspapers, traveling on vacation, live music shows, going to bars, listening to music. So that's a very active lifestyle. While class 1, 25% of the sample have the lowest incidence of any activity of all of them. A very kind of, I don't know how to describe it, a group that has no life. Class number two, which represents the majority, 41%, they are more likely to do gardening, going out with family, and attend religious service, a more family oriented lifestyle. And here on columns O to S, we have the classification probabilities, the posterior probability that each of the consumers belong to each one of these three classes. And that's pretty much how you can do latent class analysis using my analytic tools for Excel.